Hey everyone, thank you for joining us for Pure Virtual C++. My name's Anna. I'm an event planner for Reactor, joining you from Redmond, Washington. Before we start, I do have some quick housekeeping. Please take a moment to read our code of conduct. We seek to provide a respectful environment for both our audience and presenters. While we absolutely encourage engagement in the chat, we ask that you please be mindful of your commentary, remain professional and on topic. Keep an eye on that chat. We'll be dropping helpful links there too. Our session is being recorded. It will be available to view on demand right here on the Microsoft Reactor channel. With that, I'll turn it over to our MC for today. Sai, take it away.
Hey everyone, welcome to Pure Virtual C++ 2025. I think this is our 5th year running this conference, and we're going to have 5 talks for you on a variety of C++ subjects. We're going to start off with Inbal Levy, who's going to tell us about static reflection in C++, with welcome to version 1.0 of the metaverse. Then we're going to have Mingxing Wang talking about Proxy and next generation polymorphism. We're going to have Sinem Akinje talking about GitHub Copilot and how it can make unfamiliar C++ code familiar. We're going to have Cameron DeCamera talking about C++ modules myth busting. And then we're going to finish off with Hanna Dushkova talking about Constexpr everything, ? So we're going to get straight into our sessions today, starting off with Inbal on the metaverse with static reflection in C++. Take it away.
Hello, everyone. I'm very excited to be here today and talk to you about reflection, and I hope you're as excited as I am about this feature. So welcome to version 1.0 of the metaverse. So for those of you who doesn't know me, my name is Inbal Levy. I also put here a QR code for you to be able to scan, and also the link so that you can follow the slides. This talk contains quite a lot of Godbolt links so that you can experiment with, and I'm sure it's going to be more interesting to review it this way. So please feel free to enter the slides. Meanwhile, I'll tell you that I'm a C++ software developer. I also am very excited to be here in Pure Virtual as I recently joined the OS Internals group in Microsoft. I'm an ISO CPP Foundation and Boost Foundation board member and active member of the ISO CPP committee. So the CPP committee is the one that is in charge of basically publishing the C++ standard every 3 years. As part of my roles, I'm the Israeli National Body Chair and Library Evolution Workgroup Chair. So Library Evolution is the group that is in charge on the standard library design of the standard library. All right, cool. So what is reflection actually? Reflection is the ability of a software to expose its internal structure. And the idea here is that you have a program and you can observe another program. So when I talk about reflection in C++, and by the way, in Rust as well, I'm talking about static reflection. You may be familiar with reflection from Python, but that's not the case here. So we're talking about compiler that basically looking at our reflection syntax, translate that into a valid C++ syntax, and then this is being compiled to a binary, and there's nothing left in the binary to indicate that it came from reflection. So of course, this addressed concern like performance or security, but also it's possible for users to basically write their own code to preserve this information, but that's not part of the feature in any way. And this was discussed also quite heavily when this feature was first starting to become to come to existence. So, sorry. We have 2 parts of this talk. First part is intro to reflection. I'm going to go over a brief history of the reflection proposals in C++. Go over the latest proposal, that is P2996, one that is slated for getting into C++ 26. And at this point, I want to mention that we are in a very interesting point of the cycle of the standard. So we have basically what is called feature freeze, and that is we already finalized all the features that are planned to get into C++ 26. but we're now finalizing the fine graining and finalizing and fixing bugs and things like that, addressing reported comments, that is NB comments. So until the document is signed, we cannot know for sure which features are going to get in, and that's going to be sometime next year. But still, I'm very optimistic regarding the reflection proposal because it got a lot of support. So when I say it's going to land in 26, if I say that throughout the talk, please take this with a grain of salt, as it haven't been signed yet. I'm still I'm very let's say I'll be very surprised it will be pulled away. So latest proposal, as I mentioned, we're going to talk a bit about the complexity of reflection. And the second part is going to talk about the impact on our code bases. So we're going to look at reflection-based libraries, some examples, and talk about what's next. Another thing I wanted to point out is that the examples here, that you can use, to get into the Godbolt links and experiment with, have been basically derived from the P2996 paper. And I also want to point out the Wire Charles and David van der Voorde, and that led basically implementation for EDG compiler, and Dan Katz from Bloomberg for leading the implementation for Clang compiler. So thank you very much to those people for working on those implementations, because that what allowed you to experiment with and enjoy, even before the feature have been published officially. So let's start with a quick brief history review. So in 2006, it was the first time I've recognized the reflection being mentioned in context of C++. And that was for by Matul Konchik, that had a mirror reflection library. This library was heavily related on template metaprogramming, with techniques that you are familiar with. In 2012, we had a paper by Mark Spartus, and he tried to enumerate use cases for reflection. So again, things like getters and setters, serialization, wrapping types, and customization point. He didn't call that in that term, but that was the intention. So that's very interesting to follow up and see what actually made it and what actually is supportable by the proposal. I'll give you a hint, not everything that I mentioned is directly supported. Between 2014 and 16, Matush was trying to standardize his library. And again, that was multiple papers, and as I mentioned, having a proposal requires some process in getting into the standardization. But in 2015, we had an implementation of Boost HANA by Louis Dion, and that was a template metaprogramming library and heavily relies on template metaprogramming. And at that point, it became clear that template metaprogramming is not necessarily the best tool to achieve reflection from two reasons. One is that the error messages from template metaprogramming is not necessarily indicative, and it can instead of coming from the logic, it can come from the technical implementation, which makes it harder to basically for developers to use. But the second more significant problem was that the compiler had a hard time. Compilers had a hard time basically implementing that in a way that will be feasible. So I used to work on a large project, and the linker were failing to load all the symbols to memory, and that was not even a significant project as others might be, like, for example, the one I'm working on now, which is the OS Windows source code. So at that point, it became clear that we need a different tool, and the different tool was specialized syntax. So we had a few proposals trying to suggest the specific syntax, and we also had the term meta object coming up. So I'll go back to that, but I just wanted to also highlight the fact that in 2018, we already had a proposal or paper in the domain of reflection by Bjarne Stroustrup, the inventor of C++. So you definitely can see that this feature is getting more and more traction. We had Reflection TS by David Senkel. TS is a technical specification, and that's a document tries to basically clearly specify all the details of a feature. And we had, again, going back to the term meta objects, we had some arguments about type-based versus value-based, etc. So I would explain on that a bit. So if you want to represent your program, let's think about the program as a project. You'd probably think of like as anything else, any other program that you write that tries to represent information from the real world, you're probably going to consider hierarchy as one of the options. So you could like consider things like creating a type that is a function and then inheriting from that for a static function or member function, etc. But that turned out to be quite heavy again for the compilers, because then they had to preserve this to have this full our hierarchy model to save of all the entities in the program. By the way, it's I will refer to that further, but then we settled for something that is a single object, that is what is called value-based reflection, and that is what we now have as stud meta info object. So also Constexpr was also around that time was getting more and more support, more and more things became Constexpr, but still Constexpr by itself is not enough to basically have a generative code. So in 2020 and 21, we had some discussion on syntax and naming, naturally. And we also had another paper talking about the value versus type-based. But in 2023, we actually had our reflection proposal, the one that, as I mentioned, slated for 26. And I want to mention the authors: Barry Razvin, Wyatt Childs, Peter Dimov, Andrew Southern, Faisal, I don't remember your last name, sorry, and David van der Woede. Thank you very much for working on this proposal. I'm very, very grateful, and I think the community also is very grateful. We had a few more proposals trying to basically utilize the syntax that is being proposed and apply that to use cases like binding and also observed some bug fixes that I'm going to refer to later. But today we're going to talk about the latest proposal 1.5 years later. We are now at revision 11. So what do I mean by reflection? I already gave you the general terms, but now I want to give you a bit of code snippet. So we have here a library type. It inherits from base 1 and base 2. And here we have this reflection expression, and we basically take this lib type that we defined, and we lift this using the lift operator to reflection realm. So of course I'm using this terminology. It's not in the standard in any way, but I'm using this to emphasize the ideas behind this. But now we have this stud meta info object that represents lib type, and I can put this expression in meta function. So this is stud meta basis of, and basis of would return as according to the name a vector of stud meta info objects that is the basis of the class, and this is according to declaration order. So if I reach out to the first element of the vector, I'm going to get base 1. Cool. So the reflection paper, now that you know what it is, basically have four main parts. The reflection operator you're already seeing. Splicers, which is if reflection operator, lift operator is basically taking things from C++ realm into reflection realm, splicers take them back to C++ realm. We have stud meta info object itself being proposed into the standard, and we have a bunch of meta functions. So I'm not going to go over all of those meta functions, but you can already spot some names that might resemble type traits. And the reason is that we've basically it was a lot of discussion, but those all are under stud meta namespace and not the type traits on traits. And the reason we added them is because those can get compiler intrinsic support and basically work better with the reflection utilities. So it's definitely resembles that, but it's different implementation, or could be, because the spec never talks about implementation, but definitely allows that. And we're going to see, I hope, in the upcoming years, the impact of that. So we also used to have reflect expression, and it turned out that constant expression is too much to promise. Therefore, it was replaced with reflect value, reflect object, and reflect function. And define aggregate. For those of you who have been, if you have been following the proposal, at some point it had define class. Define aggregate is an extension. On top of that, it can, on top of defining structs, and it can define arrays and unions, etc. All right, cool. So lift operator. So we used to have a single caret, and then basically to avoid ambiguity with other language, we had to turn this into double carets. So if you want to use the nickname for that, you can use Unibro, which was suggested by JF Bastain. He's the chair of evolution work group. So as I mentioned, I'm the chair of library evolution. That's the group in charge of the standard library. Evolution is the group that is in charge of syntax of the and the programming language C++. So I'm really grateful, and there was a lot of collaboration between us. But yeah, feel free to use Unibro, just give credit to JF. But going back to our operators, so this line that you see here, I'm taking an int, which is a type in C++ realm, and I'm basically lifting it. But this line doesn't work as is. And if I could take hands from you, probably have multiple guesses or multiple answers. I'm sure some of you would have catched that, but I did mention that quite extensively already in the beginning of the talk. We have to have things that are available for our compiler to execute on. So the reflection expression itself have to be Constexpr, so that the compiler knows it can activate logic on. So now it's fixed, and again, we can take the things into reflection realm and then splice them back using this operator that you see here, back into the C++ realm. So the type name here is the canonical way to use splicers, because when some cases, you might need to disambiguate that and make sure the compiler understands that this is a type and not something else. But generally speaking, you don't have to use type name. You could use splicers in the general case, and only use this for disambiguity. But I did wanted to give you like the canonical way to in case you want to experiment that later. So yeah, now we're taking things back from reflection realm back to the C++ realm. So let's do a small recap. What is reflection expression? Reflection expression is the meta info object that represents int. And what is, again, ignore this typing for a second. What is reflection expression in splicers? Well, this is just an int, right? I'm going back from this to that, and I can actually declare here int a equals 42. That's what happens here. So again, if you want to read a bit more about the type name and disambiguity, please go into this link. It's really specified well in the proposal. So we talked about reflection operators, splicers, and meta info. Let's talk about something else, a bit more information about meta info, and then go back to our proposal. So what we have here is what is called AST of Clang compiler. So AST, for those of you who have taken compiler course or just explored on how compilers work, AST is an abstract syntax tree. So this is basically when you take a C++ program and you parse it, you want to represent the program in some kind of a model, a programmable model that you can actually use. So you have here basically things like function declaration, that's our main, variable declaration, I, which is the name, and int, which is the type, and the fact that it's an L value, etc. So I hope you now see some connection between the student meta info and what I mentioned about the information about reflection. So and the AST. So definitely std meta info can contain type and type aliases, functions, variables, etc., enumerators, template namespaces, and so on. But you need to pay attention to those two lines. Object that is a permitted result of a constant expression, and value that with structural type that is a permitted result of constant evaluation. And the second one should probably resembles, for those of you who are familiar with NTTP, non-type development program, this kind of restriction resembles that. But we used to have a restriction for constant expressions that was discarded in quite early stage of the proposal due to the fact that we found out that making promises for expressions in general is a bit problematic due to side effects. So long story short, that's an error on what was in earlier stages, but we can always extend proposals later or add on top, but it can't take back promised usability. So again, looking at this example quickly, we can see here that I made the reflection operator Constexpr, but also this would not work because I have here an int, and I need to have something that the value that I want to reflect on have to be available at compile time. So that's again emphasizing what I said before. So yeah, let's quickly talk about some meta functions. So again, the idea of meta function is that I can take something, I can lift it, and then I can operate on it. So this is an update for basically the latest state. And the latest state we used, instead of name of, we modified the name into identifier of. And the reason is that in C++, names are, they can be context dependent. And like, for example, you can have a fully qualified name with the namespace or something else. So instead of going in that direction, we modified it to identifier of to make sure we don't clash or close the design space in the future. So all meta functions take info, or apart from those three that I mentioned here, they take the type, and return string views, std meta info, vector of std meta info, boolean, size t, source location, etc., and member offset, which is a type that we define for bit fields. So let's we talked about reflection, and let's talk about a bit about some interesting non-intuitive things that we have in this proposal. So I have here a class. I have a declaration of a class. And for those of you who are not familiar with the term complete type, is that I can declare a class and I can define it. And until the compiler knows what's the structure of this class, it's going to be considered as incomplete type. So I declare the class, I lift it to reflection realm, I use this expression to give it to a meta function, and I query is complete type. And at that point, you probably can guess that this returns false. So now I look at this class after being defined, and I do the same thing again. I take a reflection expression, I execute is complete type, and I get back true, right? Because at that point, we already know that this have been completed. But the question is, what am I going to get if I'm taking result one, the one that we've defined in line 6, and execute the function here? So the two options are true or false. And the option that is here, naturally, as I'm showing this to you, that is as something that is less intuitive, I think, is the fact that this would return true. Because despite this looking like a value that we're taking, or a snapshot of the AST, that's actually more like a reference. And I want to use the disclaimer that the standard never tells, like, compiler implementation is not being defined. So when I say a reference to AST, that's not in any way obligatory for compilers to implement that way, but I want you to get the logical idea of how this works. And this res1 is basically describing a state of an entity in the program, but at that point, the state have been modified, and that's not a snapshot of where the expression was taken, but basically an information on this entity that now is actually complete. So we're going to get here false, true, and true. There's two types of type traits, one that query a type and one that modify a type, like remove serif would be one that modify. And the main focus of the current proposal P2996 for 26 is to move away from things that modify it, and exceptions to that is define aggregate, and of course you can splice, so you can modify the model, but generally speaking, as there were more controversy or was more challenging to convince all the parties that are involved in getting the complex aspects of like modifying your ST, where you're evaluating it, etc. It was both a pushback from Copilot implementers and also from other people in the committee that wanted to get more information before we do something that is more adventurous. So that was basically pushed to a later stage, but it doesn't mean that we're not going to get those kind of traits in the future. And I'd love to hear from you, especially if you have ideas for things that you think that we need. I would love to hear from you, and I'm going to give my email at the end of the talk. So please feel free to reach out, and I expect those to come up in the upcoming years. So another important point to make is that using reflection, we're used to have in C++ access modifiers, and using reflection, we can actually access private members as well. So we don't only access, but we can also assign to it. So the idea is that, as I said, the intention of the feature to be able to represent the structure of a program, and private members are also part of the structure of this type. So hypothetically, we could go the other way and decide that we're not exposing the private, and there was a lot of discussions on those as well. This is supposed to be, but we could also take the path of, for example, Java, that had at some version explicitly marked the classes that are being reflected on by the author of the class. They could opt into being reflected on, but that was not the case here. And I think the design options are all kind of all the options make sense, but this is the direction that we went through. So I want to summarize everything that we saw so far. So I wanted to show you also a bit of a example of a potential library that we could have. So first of all, I defined here a const eval function, log members. It takes some meta info. And then I can, of course, I need to probably do some checks here, as I would with other functions as well. But then I can basically print the name of this thing, and also iterate over the non-static data members of, and print them. Note that this is report Constexpr value is like intrinsic of EDG. It's not part of the proposal, but let's execute this code on this struct student. So we execute this and we get exactly as expected, name of the type, and then member and another member, the names of them. So, but what about AI? So you could consider reflection as something, as a tool that gives you the ability to generate code. So naturally, the thing that you might think of is we have AI, we have generative AI. So maybe that could replace the need to write explicit code that's going to be generated. So I try to explore this a bit. And of course, I want to, disclaimer is, the very important disclaimer is that the world of AI moves really fast. And what I've tried to explore today is not the same as what I might get in the future. But I use this prompt, generate my type serializer class in a header based on my type, which provides serialize and deserialize methods for my type, turning it into a buffer and back into my type class. So first attempt, I got back from serialize a type which did not fit to the input type for deserialize, and I consider this as I consider this as a design flaw. So I asked the model to modify, and I went through a few iterations, and I got to something pretty reasonable. But then I wanted to do this experiment again because I wanted to check for consistency. So I did this experiment again in a different basically workspace, because when you open like in your IDE some workspace, the agent can actually, and you use the extension, for example, Copilot, it can preserve some information, like cache some information on the previous operations, and I wanted to like make sure I start from scratch. So a different project. Then I don't get the problem that we saw earlier, but I do get like other APIs and interfaces, which means that if I would try to put this in a pipe and try to generalize or try to like automate this, I would get different result every time. And I also would not know how to like automatically fix, because there's no input that I can give that is consistent enough throughout different iterations. Now, I would point out that if you give the example, like for example, like if you give a template example to how you want this thing to work, once you already like you have this example and already created existing in class, and you just tell like the LLM just do the same thing for this class, it works a bit better. But still, there's no determinism between different executions. So long story short, the way LLM works is by trying to guess, the best fitting text is non-deterministic somewhat inherently. And especially when I start replacing like models or extensions. By the way, for those of you who are not familiar with this, as part of my role in Microsoft, I've been working on also getting more of our group to use AI tools, and I've been exploring and studying a lot of the extensions, etc. But when you replace extension, you basically every extension or every tool can define its own system prompt, and the system prompt is being wrapped around the prompt that the user used, and therefore even if you go into the same model, for example, querying the same model, if you pick the same version, even it doesn't necessarily promise you that you're going to get the same result, because the system part might be modified as well. So long story short, definitely when we start modifying things, but also between different executions on the same platform and with the same model, we might get different results. Again, so no guarantees between executions, but that's as of now. So again, the world of AI develops really fast. Could be that in the future it will be consistent enough for us to rely on for automated tools. But the underlying point is that once you use deterministic, like feature-like reflection or frameworks like Jinja that generate code basically based on templates, you have the determinism is being guaranteed, unlike with AI. Another point I wanted to make is Rust. So I'm sure you all know that Rust and C++ are both had a lot of discussions in the latest years, and I think Rust is a great programming language. By the way, I think we have a lot of shared and common use cases, and we can collaborate really well to improve both languages, and I think that's what we're already doing. So Rust, does have some abilities to do reflection. It have macros, but it also have the sync library, which is basically a library to inject tokens into AST. It have procedural macros, basically used to process one AST into another. And I've put here a table that tries to summarize what I consider in terms of how Rust works. But I already talked to you about a bit of the AST, etc. And in my mind, having code that is basically on the level of application code that tries to reflect also need to deal or modify the AST is breaking of layers of encapsulation of the logic of the program. So in that sense, I think that C++ code, as of now, the reflection that we are now having proposed, is actually a very good way to keep separations on responsibilities. And in a sense, someone in the Rust community have agreed with me because first of all, they have been watching closely on what we are doing, the C++ programming language is doing. But second, they actually created around a month ago, there was a publication, official publication, as far as I could find, or the list. It's still experimental, but at least the most up-to-date and most complete publication of ReflectLib. And ReflectLib is trying to basically get avoid or get rid of the boilerplate and edge cases and things like that that are needed if you use SYN directly, but it's still working on the AST, working on modifying the AST. So I think in that kind of scope, Rust could benefit greatly from also taking or having some syntax that is specialized for reflection. And I think in that aspect, C++ is doing a great job. I will also point out that we have, as part of the standard committee, we're currently working on starting a combined group between Rust and C++. That's like going to talk about the interoperability and other things as well. And that's in collaboration with the Rust Foundation. So I'm really, really excited about how those two languages are going to be able to communicate and develop in the upcoming years. So to summarize, what can we expect from reflection libraries? As I showed you, once we start getting into reflection, exposing to you the internals of implementation, we cannot have any guarantees between standard version in terms of reflection, of course, not in terms of C++ in general. And there's no backward compatibility. If the source code have been modified and you execute even in the private members, for example, you execute your reflection logger, you cannot expect the result to be the same. So the outcome of breaking this can either be the program does not compile, ill-formed, or it's UB. But we try to do better. And for doing better, I actually need to mention here Hanna Desokova. She worked on Constexpr exceptions. So it may sound weird at first, but those exceptions do not leak to runtime. And the compiler basically can use those to signify an error better than the current mechanisms that we have. So I think this is a really good step forward in terms of error handling, error reporting. And that's, by the way, not just for reflection. It's also for anything that is compile time executed can use those. And also interesting to think of how warnings might come up in the future and improve the way we read this code. So here's a quick summary of the talk. We had a brief history of reflection proposal, looked at the latest proposal, talked about the complexity and the non-intuitive cases, talked about reflection-based libraries, and maybe what's next. And I would love to hear from you which reflection libraries you think should go into the standard library. Please feel free to reach out and give me more information and talk to me about that. And that's exactly the kind of input that I'm looking for. One more thing I wanted to point out is Daisy Holman. She's a committee member as well. She recently joined Anthropic, and she gave a really good talk around 2 months ago about how models work and how LLM works. And she also did some really cool experiments in regards to C++. So the video is not available yet, but the slides are, so I linked them here. Please check that talk out if you want to learn more about LLMs. So I want to thank Core CPP user group, our local user groups, who are seeing early versions of this talk. To Hanna Desokova, which is SD7 chair. So SD7 is the group that is in charge of compile time inside the C++ standardization committee. This is like an incubator, and have been incubating this proposal until it got to the design group. So thank you very much for her contribution as well. And by the way, she speaks in this conference, so you can also use this opportunity to send her a message and thank her. To Matush and David Sankel, Karantan, Lewis, and Adi for reviewing this talk, and to all reflection papers authors, not just the main proposal, but also all the ones that contributed fixes and gave feedbacks and so on. Thank you for being passionate about C++. Please stay in touch and feel free to email me. And I also want to thank Sai for organizing this great conference. Thank you very much and enjoy the rest of your conference.
Thanks very much, Inbal. I find that talk really interesting. Metaprogramming and reflection have always been a key interest of mine, so I'm really excited to see where this is all going to go. Inbal will, I think, be in chat in a bit to answer any questions you have, or you can also email her on the email which was in the slides. we're going to just go right on ahead to our next talk, where Mingxin is going to be telling us about Proxy, the Proxy library, and how dynamic polymorphism can now look in C++. Let's go on ahead.
Hi, everyone. I'm Mingxin Wang, Senior Software Engineer from Windows Essential Experience team. I have been driving this project for several years. I also drive several projects within the Windows team. So this talk is about Proxy, and the title is Next Generation Polymorphism, which is also the title of our GitHub repository. So before we get started, I would like to show a little bit appetizer. So if you look directly into this code, this is the code you can write with the next version of Proxy, not the current version. The support pro skill syntax is for the next major release. So let's keep go a little bit inside the code. So basically, we include Proxy header file because Proxy is a header-only library. You just include it. You don't need to link anything. Then you define a struct formattable. It's actually called a facade. Basically, define it with a facade builder. Specify it supports a format skill, and then build it. Then you have a type. This type is an empty type. It's a meta type. With a meta type, you can instantiate a proxy object and assign anything to it, like P1, P2, and P3 are all proxy objects with the same type. But underlying, they have different types. Like the P1, the type is constitute string, pointer of constitute string. For P2, the underlying type is unique pointer. For P3, the underlying type is the return value of make proxy. Actually, the small buffer optimization automatically happens behind the scenes because the number, the double is small enough to fit in the buffer. So basically, we define 3 variables, and we can use them as the same type, proxy. For P1, we can simply print line and put it in the function, same as P2, same as P3, and the output is exactly the same as the original type. You cannot do it with the C++ syntax today or in other languages. Like in Java, you have to override the toString function in the object base class, so as C#. But C++, you don't have this option. The only thing you can do is to define a virtual function on some type and invoke the virtual function. It cannot integrate precisely with a complicated library like std format library, but you can do it with Proxy with just a single line support pro skills format. So for the rest of the talk, I will dive deep into what the 3 lines actually do. Okay, this is the overview of the talk. First, we will talk about the motivation, basic introduction of the library, some benchmarking numbers, the basic concepts, what is Proxy, how to create it, and what prototypes you get, how to build a facade, and the last topic is skills. So we will basically cover every aspect in this overview of this talk. So first about motivation. The motivation is actually, I don't have multiple slides for this because, not because the motivation is trivial, but there are a lot of research about the motivation, especially the second bullet point. Virtual function in C++ has certain limitations. There are 3 talks. I highly encourage you to watch it if you haven't. So the first motivation is that we do want runtime polymorphism. It's a useful paradigm. Although we have std variants in C++ 17, and a lot of template facilities, also reflection. But without runtime polymorphism, certain things cannot be implemented. So it's a useful paradigm. And the third one is the existing polymorphic wrappers in C++ are not sufficient. I specifically mean std function. And there are other polymorphic wrappers like std move only function in C++ 23 and std any in C++ 27. But the most widely deployed type should be std function. You might find std function is very useful in a lot of cases, but apparently not sufficient enough, at least compared to other facilities in other languages. So ultimately, we want to write polymorphic code as easily as in Java, C#, Go, or Rust, or any other languages. We want to make C++ better while keeping the C++ quality. So this is our ultimate goal. And as far as I know, Proxy is the only library that has implemented this feature. So a little bit about the background. It's open sourced. You can just navigate to github.com/Microsoft/proxy and to get the whole access to the library. The title is Next Generation Runtime Polymorphism in C++. It is licensed under the MIT license. You can use it freely for business or non-business. It's portable. It's header only. Before the 4.0 version, it's a single header library. But in the 4.0 version, it's not a single header library. It has another header that can interact with the FMT library if you have used it. Just similar to the appetizer I just showed you, you can integrate it smoothly with the FMT library with just a very tiny header. And it's non-intrusive. Why non-intrusive is good? There are a lot of talks about this. I don't want to go deep into this topic. And this one is the most loved feature. It's well managed. What means well managed? It offers GC-like behavior. It actually offers different lifetime management model for each object, while the performance is not affected. But the behavior is similar to there's a GC behind the scenes. And the next one is fast. That's absolutely the key feature of C++, and we don't want to break it. In our benchmarking, you will see it's even faster than the built-in virtual functions. Accessible. It's a simple word, but it requires a lot of effort to implement it. The accessible includes diagnostics and API design, and ease of use, ease of learning. And it's also flexible. Any paradigm like inheritance, combination, and RTTI, all the paradigms can flexibly combine together. You can refer to the proxies frequently asked questions or proxy specifications. This specifications is for 3.3.0. And the version I will demonstrate in this talk is not yet released, but we plan to release before the Build conference this year. A little bit background about this library. Is deployed in Windows since 2022. It's now available in both VCPKG and Conan. We initially published it in August 2022. You can see my blog post. We also have an announcement for the Proxy 3, the 3.0 version. I'm also a member of the ISO C++ committee. I also have 3 papers for this library. If you are interested, you can just download them and read them. It's initially open source in 2022, and the latest stable version is 3.3.0, and you can acquire this version both from Conan or VCPKG. And the next major version is Proxy 4. If you are using Proxy 3, you may experience API breaking change because we have improved the code generation. It offers better API and better diagnostics. But within a single major version, the API is considered stable. So let's talk a little bit about benchmarking. So we advertise it as fast. So how fast is it? We have automated our benchmarking in November last year. We test over 5 major environments, include different compilers like MSVC, GCC, Clang, Apple Clang, NVIDIA high performance computing, and on different platforms like Microsoft Windows Server, Ubuntu, latest version, Mac OS on Apple Silicon. And we compare 20 metrics. You can just navigate to our pipeline and can acquire the report for each run, download it, and you can see the number. So this is the number I got from the latest recent build. From the indirect invocation, you can see MSVC is much faster than virtual functions. For small objects, it's even 300% faster. And for on Apple Clang on Mac OS, on the ARM-based chip, the advantage is not that significant, but we still see a difference between proxy and traditional inheritance-based polymorphism. We also tested NVIDIA high-performance computing. Number is a little bit different from other platforms. Different compiler will translate proxy into different machine code, but they're very similar. This is a part of the P0 lifetime management metrics we have today. You can see there are some red points, which is proxy is somewhat slower than like on Apple Clang on macOS. It's a little bit slower for compared to StudAny for lifetime management. We found the libc++ has some optimization in that, so we simply didn't do the optimization, but we can do it better if not optimized for general use. And other metrics look pretty good, especially on Windows. So the concepts. This ASCII diagram is the concept tree of the proxy library. It's based on facade. Facade is the overall abstraction of runtime abstraction. So it's an abstraction defined for abstraction. Within facade, we have convention types, which is the member functions, like stud format integration, and like proxy cast RTTI. And reflection allows you to embed any metadata to proxy library, and it will become super useful after C++ 26, because at that time we have a very powerful reflection infrastructure like Imbo just introduced. And the third one is constraints. A set of constraints for pointer types. It includes maximum size, maximum alignment, copyability, relocatability, and destructibility. Each of the capability is a value of constraint level. There are 4 constraint levels in C++. The most relaxed is none, and non-trivial, then no through, and trivial. If you are familiar with type traits, you will see the type traits always named with the 4 constraint levels. And in this library, we abstract it as a enum constraint level. So if you browse the library, you will see there are several concepts. The first concept, facade, is just a diagram I just presented. So it specifies that a type models a facade. There are 3 other concepts. Proxyable means a pointer type meets the requirements from the facade. Proxyable target specifies a value can be instantiated with a proxy view, which is the strict term of the proxyable target. You can simply take it as a type that has implemented all the indirect conventions. So in-place proxyable target is a stricter requirement than proxyable target. It specifies whether a value type can be instantiated within the footprint of a proxy object without allocation. It's useful, especially in embedded scenarios. So, proxy. This is a very rough overview of the proxy class. It's incomplete just for exposition. So a proxy inherits a bunch of accessors, and it offers indirection and dereference for all the 4 reference types. The memory layout is basically a vtable, similar to a virtual function. But the vtable could be embedded inside the proxy object if it's small enough, like it only has 1 function or one reflection or 2 functions. In this case, the vtable can directly embed into the proxy object and theoretically improve the invocation performance. And we did measure that in our benchmarking. So the second field is a byte array. It's aligned with the constraints maximum alignment, and the size is the maximum size. So you can basically put any pointer that's smaller than the size and the alignment is smaller or equal to the maximum alignment into this buffer, and it can hold it. It can mimic the exact behavior of the pointer. So these are the 4 key types of the proxy library. So proxy is the base type. It just, as I shown before, it wraps a pointer object matching the specific facade. It has 2 variants. The first is proxy view. Proxy view is an alias of proxy. The definition is actually proxy of observer facade. For another important type is weak proxy, similar to weak pointer. If you are not using inheritance, so basically we do not encourage you to use C++11 smart pointers like unique pointer or shared pointer wrapped with a polymorphic object, and we just recommend you replace them with proxy. So let's see the basic definition of proxy. You can see the online documentation. These are the member functions. I won't go deep into that. Here's some comparison. For each documentation, we have examples. Like in this case, we define a member dispatch. You can basically take it as a member function definition. And we add a convention. the convention is the input type is int, output type is string. It actually forms a member function at, and the name is mem@. You can basically create a library. Here I have a very tiny library. It takes a directory. I don't know the actual type of the directory. All I need to call is to just call pointer at, because it supports this operation. I don't need to know the underlying type. This function is not a template. It's a concrete type like std function. And from the client code, you can see we have two containers. One is a static map. Another one is a shared pointer of vector. We can put all the two types into this, implicitly convert to the proxy object and use it as if using the original type. And we just mentioned proxy view. Proxy view is just an alias of proxy. And you can define a proxy view of some fmap. You add a convention, the bracket operator. Input type is a key type. The return type is the reference of the value type. And you can invoke it as if invoking the original object. But the difference between proxy and proxy view is that proxy view never takes the ownership of the original object, similar to a row pointer. And this is, like I said before, similar to a std weak pointer. You can define a shared pointer and convert to a weak pointer, and you assign to the weak pointer to the weak proxy and lock it. Then you can just use it as if using a weak pointer. Okay. And that's all about the proxy itself. So how to create a proxy? We offer several creation functions. Also, you can create from a row pointer or any smart pointer, but we recommend you use the creation functions if possible, because they usually offer better performance, especially like make proxy shared is similar to make shared. Make proxy view is similar to just assigning a pointer to a proxy, but it honors reference. We can see a little bit about these types. Make proxy, similar to make unique, but it actually can allocate the proxy within the footprint of the proxy object if the object is small enough. And make proxy share similar to make shared. But if you are sensitive about space, you can observe on major platform implementation, shared pointer is usually the size of 2 pointer size. So that if you have a facade and you want to restrict the layout to just 1 pointer size, still shared pointer won't work. But make shared proxy will still work. Allocate proxy is similar to allocate shared, but similarly, it offers better performance. Make proxy view just like the borrow semantics in Rust. So let's come back. We will cover a little bit about the other parts, like dispatch prototypes. There are 7 dispatch prototypes in the library. Conversion dispatch is split into explicit conversion dispatch, also alias to conversion dispatch, and implicit conversion dispatch. Operator dispatch, you just saw, we can define an operator of brackets or other operator, even include comma. We also support that. weak dispatch is something you want to have a default implementation, and if it's not implemented, it will just throw not implemented, but it will not generate a hard compile error. There are 3 macros here. The reason we use macro is because C++ does not support generating a member function with an arbitrary name, as we just saw, like the add function. We cannot simply provide a string literal add and ask the compiler to generate a function named add. We don't have this capability in C++ 26, but hopefully we can have it in C++ 29. So at that time, we can get rid of those macros. Facade builder is all the magic happens within this type, because you can see the definition of facade is very complicated. Without a builder, it's very hard to write a correct facade, and the builder will help you to write and combine all the abstraction you have defined before. Let's take a quick look at the documentation. Here's the operator dispatch, and we define many operators, all the operators supported in C++. And these are the macros. We define the dispatch types. You can also give it an alias. It supports 2 syntax. You can give it a function name, and it just generates a function with the original function name. And you can also rename it to another name. And free functions, it will just go through ADL, like we have an example here. Like you can convert a toString into the toString free dispatch, and you can invoke it with toString without any qualifier, because it can find the function through ADL. And this is the facade builder. It has many documentation, but we will update it for the next major version. Here's a very tiny example. You can simply implement a std function and std move only function in just the simple lines. And you can simply invoke it as if it was invoking the original objects. Similar to std function, but you need a star here. That's the only difference. So skills, this is the last thing I want to highlight. This is the new feature in the next major release. We haven't announced it before, and we're announcing it in this conference. We have 5 set of skills. You can convert a proxy into a proxy view with sview, and you can convert to a weak proxy with sweak. You can make it support RTTI, like RTTI in std any with RTTI, direct RTTI, indirect RTTI. With specifying this, you will get 2 functions. One is proxy cast. You can cast anything, cast to the original type, like std any cast. And you have proxy type ID, like the standard type ID. And the format, W format, you just saw that before. And in this new version, we also have FMT format. You can integrate smoothly with the FMT library if you prefer to use that library. So the last thing I want to do is a quick demo about how you can use the support pro skills syntax in the code. I just use Visual Studio. You can use any IDE you like and any compiler. But this is not the code you can run with the latest stable version. It will be available for the next major version. So this is just the appetizer code I just showed at the beginning of this meeting. I can just simply run it, and it will build. Drag the window here. See, the output is exactly what is expected. Yeah, that's all about my presentation. Thank you.
That's great. Thanks so much. Will you be around to answer any questions that folks have in chat?
Sure.
All right, great. Thanks so much for the talk. I've played around with the Proxy library a bit, and it's really great for those times where you don't want to have a template, you just want to have a function and everything to be fast. Yeah, it's great. Thank you so much. All right, we're going to move on to our next talk, where Sinem is going to tell us how to become familiar with an unfamiliar code base using GitHub Copilot. Take it away.
Hi, welcome to my talk on making unfamiliar C++ code familiar with GitHub Copilot. My name is Sina Makunja, and I'm a product manager working on the GitHub Copilot experience for C++ developers, and we have a lot of exciting new updates to our tooling to present today, designed to help you even more with your C++ code. Today, we'll explore some of the latest capabilities for Copilot. First, we'll set some context into what Copilot is and what it can do for you. Then we'll get into some of the latest advancements made specifically for C++. Following that, we'll showcase a demo of how the latest version of Copilot can assist in understanding and navigating code bases efficiently using real C++ code. After the demo, we'll review the different Copilot IDE integrations designed to meet you wherever you are, whether you're just getting started, debugging, or improving code for the future. Finally, we'll talk about all the ways you can customize Copilot to tailor it to your needs and preferences. So let's quickly refresh on what GitHub Copilot is and how it can help you with your coding as a tool. GitHub Copilot is an AI-powered pair programmer that is designed to help you write code faster. It is integrated deeply into Visual Studio and VS Code to provide dynamic coding suggestions, cater to your workflows, and can support any repo type, Git or non-Git. For example, it continuously analyzes your code to provide inline autocomplete style suggestions as you write code in your editor. There's also a chat interface that's integrated into Visual Studio and VS Code that allows you to interact with your code using natural language and ask some fundamental coding questions or questions about your code too. In the chat panel, you can also utilize different dynamic context for custom suggestions, including manually invoked context such as #include open files and @workspace to index your entire repo, but it can also automatically detect context from your natural language prompts, but we'll touch on that a little bit later. So this past year, we've been really busy. Since we last spoke at Pure Virtual Conference last year, we've listened to your feedback and focused on improving the tooling for Copilot for C++ developers. So as we all know, C++ can be a complicated language with language compliance, build systems, and several other factors at play at a given time when you are writing C++. Our goal is to ensure that Copilot provides the more relevant, accurate suggestions for C++ for your needs. And so we've invested in two key areas to improve the contextual awareness of Copilot in C++ projects, including increased awareness of C++ project structures and smarter context in chat, so that you don't need to think about all your project configurations when leveraging Copilot and can just focus on reviewing responses generated by AI and iterating. So we'll touch a lot on this new updates to context in the demo today. GitHub Copilot is also even more deeply integrated into Visual Studio and VS Code at several different points in the C++ developer loop to provide AI-powered assistance wherever you are, whether that be just starting out with understanding your C++ code base, your programming task at hand, and learning about different concepts involved with your programming tasks, to actually implementing those lines of code that are associated with your latest feature or your bug fix, and then debugging and testing your solution to ensure that it's compliant with your requirements and bug-free through making future improvements to the code base, such as refactoring your C++ code to optimize for memory performance or improving code readability and documentation for your coworkers. So let's take a look at several of these improvements to Copilot that we discussed in action today in Visual Studio using real C++ code. So here I have Visual Studio 17.14 Preview 3 installed, and I have the Pioneer Space game repo. And what Pioneer is it's a space simulation game that's written in C++, and I've been given the task of implementing a new orbital function, for velocity and energy. And so as you can see, this is a pretty large repo. There's several things going on, such as a lot of external dependencies in the contrib folder. The source folder has several different dependencies, such as like graphics rendering, and the test suite and text rendering, and lots of core functionality in .cpp files as well, and header files. And so to locate my relevant code that I would need to make updates in, I can actually utilize Copilot to help me with locating my specific code rather than having to navigate through all of this code to understand where exactly I need to implement my fixes. And so I can ask Copilot chat in the Copilot chat pane, where in the project is the velocity of the orbit function handled, and energy of the orbit function. And as you can see, it also underlined specific context. So it's going to actually invoke relevant tooling rather than me having to invoke the relevant functions and context via pound or at workspace. And so this is where Copilot has really improved some of the context to be smarter so that it can detect based on your natural language what exactly it needs to invoke to answer your question. And so you can see there's several different references and tasks done to help me get to my relevant code. And so it's telling me that the velocity and energy of the orbit function are in this orbit.cpp file, and there's several different functions that are defined but not implemented. So that looks like exactly where I need to start. So we can navigate over to the orbit.cpp file by just pressing click. And this is super helpful that it's integrated fully into this IDE, so I don't need to like search around, and it can get me straight to my functions that I want to implement. So I see that there's several different to-dos for different functions here. And so let's zoom in a little bit. I see that there's this function for calculating velocity area and calculating the orbital area. And so I want to get my bearings a little bit in this code base. And I'm understanding that there's these different parameters, and they all make a little bit sense to me, but I don't quite understand what eccentricity means. Copilot is now actually integrated into the quick info dialog so that it can help you describe any C++ symbols using relevant context and the LLM, so that if your symbols are lacking descriptions or functionalities or documentation, it's able to help me with understanding what this exact symbol does. So it's telling me the symbol eccentricity typically refers to a measure of how much an orbit deviates from being circular, often used in the context of conic sections or celestial mechanics. So that sort of helps me understand what this specific parameter means. And so I can sort of understand a little bit more about my specific parameters and what I need to implement. And so I've gotten my bearings a little bit, and now I want to actually implement my lines of code. If I go to Tools Options, I can actually see that the Copilot completions model has been updated to GPT-4o Copilot. And what GPT-4o Copilot is it's a fresh update to the base completions model, where it's been based on GPT-4o Mini, and it has been trained additionally on over 275,000 high-quality public repositories on over 30 popular languages, including C++. So this is a lot more representative and has a lot more training data that is representative of C++ and C++ code. So we're constantly making updates to the GPT-4o Copilot model, but really exciting to see that this has made its way into the product. And so I will have more accurate C++ suggestions based on this new model. And so I can go to my function and I can start typing my suggestions, and you'll see that completions pops up in line to provide me with inline style suggestions. And so it tells me what it thinks I'm trying to do, and it all looks good here. And it even makes the adjustment that I would want the orbital body or orbital period rather than the orbital period to body function based on my parameters, which makes a lot of sense. I can also navigate down to my calculate orbital energy function, and I can invoke Copilot to sort of help me with suggestions here. And so it provides me with really helpful comments and generations, and it even tells me where the source of the function that it is referencing comes from. And so this is super helpful for me when I'm trying to understand a little bit more about the functions that I'm trying to generate and ensure that it is up to the standard so I can like review that in the future. But for now, this function looks good to me. And so I'll save this all. And I'm now noticing between these two velocity functions that there's a little bit of duplicated code. And so I'd like to refactor for the future for this to be pulled out into its own helper function that these functions can call on. And so to do so, I can actually navigate back over to the Copilot chat pane and open a new edits thread. And so in this edits thread, I can ask, can you pull out any duplicated functionality that is repeated between the velocity functions, its own helper function within orbit.cpp. And what Copilot edits can do is it can provide me with an edits focused session and tell me the plan and what exactly it's doing. And so it's not necessarily just a chat interface, but it's deeply integrated into the editor to provide me with, as you can see, some inline style suggestions, which I can accept and review line by line to make sure that it is everything that I would want to achieve with this. And you can sort of iterate with this to add new functionality to your programming, and etc. And so what Copilot Edits does is it actually uses a speculative decoding endpoint that is optimized for fast applications of changes in file. But our team also knows that this can be faster and can be improved. So stay tuned for performance updates here as well. And so I see that it provided me with my new helper function. I can tap to accept that. I can accept these changes so that it invokes my helper function. And then I don't need the rest of these edits because it's not necessarily relevant, even though it's suggesting me to clean up some white space. So it all looks good. And now my code is refactored so that the duplicated functionality is pulled out into its own helper function. To improve readability for the future, I also want to document these functions since there's still a to-do and it's sort of like a vague sentence about a helper function. And so I can delete this sentence and I can type / in my case, because I have XML.comments configured for this project. And it'll provide me with suggestions for the function summary and parameter names based on the usage of these functions and parameters. So really helpful with generating good descriptions for C++ and improving it for the future so that other people understand what's going on here. And so that all looks good to me. And I can navigate up and do it to my other new helper function so that it's a little bit more specific. And so it tells me it'll do this velocity value function and the specific parameter names and returns. So everything looks good here. And so now that I have sort of implemented this functionality and documented it and refactored it to be better, I'd actually like to learn a little bit more about refactoring this function below. As I can see, there's a few different for loops, and I was curious if I can refactor this to use algorithms in this specific scenario. I'm not going to implement it right now, but I'd like to explore that so that I can improve it for the future. So I can go back over to the chat pane using create new thread, and I can ask it, how could I refactor the loop code in calc position from mean anomaly? And I can manually invoke that because I want it really to be constrained to that function rather than dynamically detecting intent to use algorithms. And Copilot Chat can look at my C++ project context and provide me with suggestions. So it's telling me I could use std generate or std findif to update my loop. So it's telling me even my code suggestions so I can review that all. And it provides me with really simple key changes that it's provided me with and the benefits of refactoring. And so this can be really helpful for like end-to-end refactoring solutions as well. And so I actually was curious based on this response, I've heard good things about std ranges, and I'm curious if I can implement that for this function. And so I'm curious, can I use std ranges instead? And Copilot can actually, again, look at my C++ project context and tell me that I do not have std ranges compatibility because I am using C++ 17. And so it sort of tells me some suggestions here that I would need to update my project to C++ 20. So I'd like to learn a little bit more about modernizing this repo to be updated to that standard. And so I can actually switch over the model to Claude 3.7 Sonnet, which I've heard has been better with multi-file refactorings and understanding architectural planning. And so maybe this can provide me with a tailored response when I'm trying to think with the context of my whole project, how I could update my C++ 20 standard. So we're really excited to announce that this model picker is now available in Visual Studio and is constantly updated with new models so that you can select the model of your preference and sort of iterate with different model responses. And this includes OpenAI models and Claude models as well. So this is all really great to see. And so I'm curious, how would I get started with updating my C++ standard to C++ 20? And it can sort of provide me with dynamic suggestions for this that might differ from the GPT-4o model. And it's really good. We recommend playing around with different models, seeing what works well for you, and seeing what kind of results you get for that. And so it's sort of searching through my relevant context again, and it's telling me that I would need to sort of modify my cmakelist.txt file. I might need to set my set CXX properties macro to reflect the new standard and rebuild my project. And it also would tell me I would need to test that, but it also saying that there might be these other potential compatibility issues that I should be aware of, which is super helpful, especially working with C++ where you can commonly have third-party libraries. And so making sure that every single thing associated with my build configuration would be compatible with this update, including my compiler. And in this case, Visual Studio 2022 has really good C++ 20 support. So this all looks good and is super helpful for me to move forward with improving my code base for the future. Now that I've sort of implemented my functionality, I've cleaned it up for the future. I've learned a little bit about more functionality that I could improve for the C++ code. I'd like to finish off by testing and adding tests for my latest functionality. And so I can actually ask Copilot to generate tests and it'll comply with my project structure. And so I'll ask Copilot /tests. And /test is a focus command that focuses on generating tests, and I can include my new function that I created. Oop, my bad. I'll just start a new thread, and then I can add this new function. And Copilot will provide me with a suggestion of how I can generate tests for this new command. And so it's looking at that reference and providing me with a targeted response for the tests. And so, it's able to provide me with these suggestions, and it even follows the doc test format, which is the testing format that this project uses, so that it really limits how much I would need to port code and adjust code that is provided by AI, because it's really compliant with my existing test structures. And so it really requires minimal porting over and just sort of the tweaks that I would want to make to it to make sure that it works. And so it ports over the function, and it even provides me with the different test cases and results for all of that. And so I can move over these tests and apply these tests for my C++ repo. And so that way my coworkers can run these tests with their full test suite and make sure that everything is working as we make updates to the existing code base, and make sure that every feature has its full test suite configured. So yeah, Copilot was really helpful with helping me get started with my first lines of code, understanding a little bit more about C++, navigating my code repository to get to my relevant task, and generating tests for the future. And so we'll go back over to the slides to summarize some of the things that we learned and upcoming update or other updates for C++. To summarize, Copilot is deeply integrated into Visual Studio and VS Code to meet you where you are in your C++ coding workflow. Whether you're just getting started out with a code base or just trying to learn a new coding problem, Copilot can help provide you with dynamic code base information at several different integration points to provide you with relevant information to help get you oriented and understand your code. We saw in the demo today how Copilot is integrated into the quick info dialog to help you with describing any C++ symbols that might be lacking documentation, and how chat can invoke dynamic context based on keywords to help search the relevant context and functions to provide you with suggestions without you needing to always manually scope that context. We didn't get to see this today, but Copilot is also integrated into Visual Studio's feature search to enable you to utilize it to find and locate any relevant C++ tooling based on natural language within the IDE. So for example, there's so much C++ tooling within Visual Studio, you can describe in natural language what you're looking for, and it can help you find, for example, the CMake configurations that you may be looking for. Copilot is also integrated into several areas in the Visual Studio debugger to supercharge your debugging process as well. We weren't able to cover this in today's demo, but you can look out for that familiar Copilot icon in your error list and light bulb, and Copilot will leverage semantically relevant context to provide you with an explanation and fix for your C++ errors. And so that way it can sort of help you with understanding your errors and resolving them. Copilot is also integrated into your conditional breakpoints to provide you with suggestions on conditions to break on. And so you can review those and see if those are relevant to your condition, as well as in multi-threaded debugging. It can help with providing you with AI-powered summaries of your threads. And so you can have that leveraged and tightly integrated into your parallel stacks window. And so that you don't need, whenever you're doing things complicated like multi-threaded debugging, you can leverage these AI-powered summaries that have this relevant context and can provide you with thread-based summaries. Additionally, when you're looking to improve code readability for the future, you saw this today, but Copilot is integrated into your doc comments, so in this case, XML or Doxygen, to provide you with suggestions in line for how you can summarize or enter parameters for that specific function. Another area where it's integrated in is the familiar rename dialog, where it can automatically generate suggestions for new renames for a particular symbol. And so you can focus on sort of reviewing these and seeing if any of these are a more descriptive or better fit for any variables, and sort of help you with that brainstorming or replacing step. So in addition to being super well integrated into Visual Studio and VS Code, we have also been working on making Copilot the most extensible Copilot yet, so that you can make Copilot work for you, your needs, and your preferences. And so as you saw today, Copilot Chat now supports 2 different modes based on what your intentions are. Copilot Chat is that general purpose conversational interface that can help you understand programming concepts, or is integrated into Visual Studio to ask any natural language questions about code, and can also help you with generating code in that chat pane so you can review these code snippets. Copilot Edits is a more focused pane for multi-file editing and refactoring. And so you can ask it questions for like sweeping changes, and it can use that speculative decoding endpoint to provide you with suggestions in your files. And so you can review that line by line, integrate it into your editor, view those previews, and you can also roll back any edits that you don't want to keep. You can learn more at aka.ms/Copilot edits for Visual Studio or VS Code, and aka.ms/Copilot edits VS for Visual Studio. We also saw in today's demo, if you would like to cater Copilot to your AI development preferences, there's now a model picker available in the Visual Studio Copilot chat that allows you to select from multiple different models beyond the GPT-4o base model. And so we're constantly keeping up with the different models that are coming in through, as AI is an ever-evolving landscape. So we have some of the GPT models as well as some of the Claude models, and you can learn more about the available models and some example workflows where they are advantageous at aka.ms/copilot models. You can also feed chat custom instructions, which is markdown-based custom context for chat to take into consideration, whether that be personal coding preferences, structure, suggestions, or any sort of additional context about your C++ code that you'd want it to take into consideration. To help you understand an end-to-end workflow where custom instructions are super beneficial, we actually leveraged OpenCV to generate a dog detector app using Copilot. And we were able to see how custom instructions were able to help us tailor our workflows and streamline our Copilot suggestions to be super applicable. So if you want to gather some learnings from that and learn more about how we did that so that you can learn more about custom instructions for yourself, you can check out aka.ms/cmake custom instructions. This project used CMake, VC package, and OpenCV. Additionally, if you have any sensitive content or files that you don't want Copilot to ever have access to, Copilot now allows for IT level configurability to exclude sensitive files within your organization. There is support available for both Git and non-Git based repos, and this is across Visual Studio and VS Code. So if you'd like to learn more about configuring, please check out ak.ms/exclude_content. So what do you think? Try out Copilot and let us know your experiences. It is now available with a completely free plan with simple in-product migration and no credit card required. You can learn more about joining Copilot Free using ak.ms/copilot-free-vs for Visual Studio and ak.ms/copilot-free VSC for VS Code. And so we covered a lot of updates for C++ Copilot today, so let's summarize. Copilot has evolved a lot in the last year to incorporate smarter, more relevant context for C++ developers to have increased C++ project awareness and context. Copilot is now even more deeply integrated into Visual Studio and VS Code as IDEs to provide you with AI-powered assistance at any point in your dev loop, so you don't need to adjust your workflows and you can leverage AI within your comfortable tooling. Additionally, new extensibility points are available to allow you to make Copilot work for you and your needs, including several different models to pick from across both Visual Studio and VS Code, custom instructions that you can use to cater your chat workflows, or if you want to exclude any sensitive content via content exclusion. So I'd like to thank you all for attending my talk. We're constantly working to evolve Copilot's capabilities for C++, so stay tuned for updates in the space. You can follow our team, the C++ team, at Visual C on X and me at Sinam_Akinja. You can also reach out to us via email for any feedback. We'd love to hear it at visualcpp@microsoft.com. Thank you all.
Thanks very much for that, Sinam. Sinam will be in chat shortly, I believe, to answer any questions you have. So please do keep those coming in chat if you have any questions you want answered. Next up, Cameron is going to be giving us a myth busting on C++ modules. Take it away.
Hi, my name is Cameron DeCamera, Principal Engineer at Microsoft, working on the Visual C++ compiler. Today we're going to talk about some common myths or misconceptions around C++ modules and give you some practical advice on how to move forward and move past these things. So without further ado, let's get right to it. Okay, let's start with a little bit of motivation behind why I'm giving this talk. The first thing is that modules currently struggle with widespread adoption. This is for a multitude of reasons, least of which being build support, but that's actually improving nowadays. However, there's still kind of like some misconceptions around how modules actually work. The other thing is that we, as I mentioned, we struggle from misinformation. And so the goal of this talk is to kind of take some of the common misconceptions that we've seen and sort of debunk them and, myth bust them, if you will. Modules really does have a bright future, and it's not just for compiling code. It's really for tooling, and I've talked about this in the past as well. And I also want to provide practical guidance for some of the unknowns that people have run into. So we're going to talk about some of the common breakage you might see with modules and how to possibly move past that. Okay, so let's dive into the myths, shall we? And here I have a picture of Plato. Plato believed that knowledge is contingent on our ability to discover it. And my goal with this talk is to arm my viewers with the knowledge of how to move past these myths. But really, to call them myths is a little misleading, and what we're really going to cover here are common misconceptions. However, misconceptions is a little less of a pithy title, so we're going to stick with myths for now. And the first myth that we're going to cover is strong ownership is not necessary. Okay, so to understand strong ownership, let's dive into a little bit of the history of strong ownership. This began back when Gabriel Dosray first created the modules TS, and he added this bullet point in the one definition rule. This essentially is telling the implementation that it is allowed to attach ownership information to declarations that appear inside of the module. He later elaborated on this idea in his CPPCon 2015 talk, Large-Scale C++ with Modules. He talked about how this ownership information should be attached within the toolset and the safety it allows for library authors. So why does it actually matter, though? This is what we actually need to know as library developers, right? So library authors get better control and safety over function names that they export. Because this ownership information is attached to the declarations inside of your module, it means that it can't clash with other declarations that appear in other modules or declarations that appear in the global module. It also creates a migration path from headers, and we'll talk about this in the demo portion, which is right now. So here's an example of a simple program where we have one module named M1 and a main in main.cpp. All we do is we call this function called the answer, and we expect it to be 42. If it's not, we return 1, right? So if we compile and run this program, we expect it to return 0 since the answer is equal to 42. And this will not be hit. And indeed, our program does return 0. So strong ownership allows us to have sort of module level linkage in the sense that the names of the functions start to matter a little bit less, and the actual ownership of them matters more at the link step. So if I look at this other module I have here called M2, we have a function called the answer, except this time it returns 41. You'll note that it has the exact same signature as our module M1 version does. In a traditional C++ compilation scenario, this would be a classic ODR violation. I have two copies of the same function with the same name and signature, and they are both defined in separate translation units. However, with C++ modules, we kind of get a pass for this due to strong ownership. So if I have a library here, this is just another C++ file where I import M2, and I create this function called libanswer. And all I want to do is I want to forward declare this thing inside of my main and call it except this time we expect it to be 41. Now we should be able to compile and run this entire program. And indeed it does compile. If we run it, we get the expected 0. And why did this work? This worked simply because of strong ownership. We have two copies of the answer. However, one is coming from module M1 and one is coming from module M2. And the strong ownership information enables the linker to resolve that conflict at link time. Another important thing to note here is the level of safety that this gives you now with as a library author, in that you can create situations like this much more safely than you could before. And in fact, in a lot of the cases, you wouldn't be able to create a program like this, or if you could, it would likely result in weird runtime behavior because the linker might select your function, or it might select another function of the same name. So if we take the strong ownership idea a little bit further, we actually, in the MSVC toolset, we allow the linker to fall back to weak ownership if it can definitively prove there is only one strong owned symbol of that name. So let me give you an idea of what I mean here. If I get rid of this lib answer, and I get rid of this, and we just have the answer here, but let's say this came from an older version of the library that you want to combine with the modularized version. So if I just have a forward declaration here, like this, and I get rid of the import, so this is the entire program now. We're still compiling both modules, M1 and M2, except this time the linker is only going to have the information that there is some function called the answer somewhere. So let's try to find it. You'll notice that the linker came up with this ambiguous symbol lookup. And that's actually expected because there are two of them. But what happens if we actually exclude one of these from the build? So let's exclude M2 here. If we exclude M2 and we attempt to rebuild again, if we exclude M2 and the library, because we no longer need the library portion, we can try to run, and we can see that this actually succeeded. And the reason is because the fallback to weak ownership, if the linker can prove there's only one of these in the entire program, which it did, since we excluded M2. If we run this, we get our expected 0 output here. And this is what I meant when I said that it gives libraries the option to migrate away from headers and still retain strong ownership guarantees with a named module. So you can combine header information with this strong ownership information and still get client programs to move forward. And two last things to note here is that, one, you can disable this fallback mechanism. There's a linker switch for that. And two, if we did define this to be something else, and we attempt to rebuild our program, right, we do get a successful build result, and if we try to run it, we get the expected output of 1, because the linker is no longer using our strong ownership symbol, it's using this one, and not the one that came from the compiled module. It's still there in the OBJ, however, the linker does not select it, because we have an exact corresponding declaration for the use of this thing. Okay, swinging back to our slide deck, coming back to strong ownership, we actually see that Clang and GCC have also come to the same conclusion that strong ownership is necessary for the success of C++ modules. This is an active pull request out to the Itanium API, which adds the name mangling necessary to make strong ownership work. Furthermore, I gave a talk back at CPPCon 2021 with Gabriel Dosray, where we covered the compiler internals and the implementation details of strong ownership in the MSVC toolset, basically how the information is conveyed through the toolset to the linker to make this feature actually work. So if you're interested in the implementation details of that, I highly recommend watching that talk. So I hope now that gives you sufficient evidence to come to the conclusion that strong ownership in C++ modules is actually necessary to make this thing succeed. And we're talking about named modules in this case. So that's kind of our first myth, and this is the confirmation that we have. So strong ownership is necessary. So let's go to the second myth, right? Hash include after import is an insurmountable problem which blocks adoption. And this is a common problem that we've seen from many customers, from many different compiler implementations. This is an ongoing problem that we need to solve. So let's try and solve it. So let's kind of start with a problem description. If you're unfamiliar with what this problem is, it kind of boils down to this. So let's consider this translation unit. We have import std and hash include print, which is the C++23 library, the format library. And we try to print line hello world. So if you go to compile this, this is the set of errors that I got from Visual Studio when I tried to compile this thing. Right? There's a whole bunch of redefinition errors. But what do those actually mean? Let's try to focus on one of them. Right? So std remove reference is a class template that is already defined. Conceptually, what the compiler is seeing from this is this kind of translation unit, right? So we have import std and hash include print. To the compiler, below that comment, we see std print line definition and then another copy of std print line. And if you were to just write this in a regular translation unit, this would be a classic ODR violation. However, the standard tells us that this is supposed to work from an implementation perspective. So as a user, you want this to just work. However, to the compiler, it just looks like an ODR violation. So what are we supposed to do? The standard actually has a little trick up its sleeve that we can leverage in order to resolve this problem. And it's called include translation. What it does is it enables us to take this translation unit and rewrite it like this. So we have import std and we have import print instead of the hash include. And we didn't actually have to change the translation unit at all. This happens under the covers. The compiler is rewriting that hash include statement for you. So let's see a demo of what this might look like and why this actually is important for resolving this bug. So here we are back in Visual Studio to talk about the problem. If I take that translation unit that I showed you before and I try to compile it, we actually get the very same compiler errors that I showed you before, right? So we have the redefined class template issue. So what we need to do is we need to take this include and somehow translate it automatically for us. And the way that we can do that is we first need a target to translate it to. And how I did this is I created this import std.h, and all it has is this. So we're going to deduplicate all of our standard library headers to import std, essentially. That's the idea. And to make it a target, we just change the configuration property of this to C and C++ compiler. And that tells MS Build, hey, this is actually a header unit you need to build as a prerequisite to building the program. And finally, we need to do one more thing. We need to go down to C++ properties and enable translate include. And one last thing is that we need to add this line to our compiler options. This tells the compiler that the print header actually points to the IFC that we just made the build system create for us. So now if we go back to our main and we attempt to recompile again, we actually get a success this time. And if we try to run it, it runs hello world just like we expect. And you could do this with any number of compiler headers. So we can do include iostream, for example. We can include vector. And as long as we keep adding those lines to this build line here, so we want one for iostream, and we want one for vector. And if we build again, we could see that our build was successful again, because all the compiler is doing is it's taking all of these headers and translating them to our import std h. It's translating it to this. Every single one of these, and that completely sidesteps the duplicated problem. Now, you still have an issue where you might want macros from some of these headers, and in those cases, you can either add the macros here, or if instead of using import std, you actually want to use the real header information, then you can just hash include all the headers in here and translate them that way. And this is actually what we did for the Office build when we moved to using header units to build Word. Speaking of Office, we went through a series of blog posts where we detailed our experiences in migrating a very large code base to use header units and eventually to name modules. This is a very good guide for anybody with a code, like a code repo of this size, looking to experience in the problems that we ran into, the category of issues, and how we solved each of those problems. And this include translation mechanism that I just showed you is actually one of the things that fell out from that investigation, and one of the learnings that we had in creating a path from textual inclusion to now a modularized and sort of like data-driven approach with these IFCs on disk. Swinging back to our slide deck now, we've gone through the exercise of making this work in Visual Studio. Now, this is not a solution that will work for every build system. Obviously, things like CMake need support for include translation in order to make that approach work. But as long as your build system has some support for include translation, you can actually create a situation where this problem is no longer an issue. So if we go back to our myths now, we can safely say that include after import is not an insurmountable problem blocking adoption, right? And finally, we come to our last myth. C++ modules do not improve build times. This is by far the biggest thing, the biggest question mark in all of modules history. So do they actually improve your build times? Because that's what a lot of people want to get out of them, is better build throughput. And, you know, despite the fact that we've covered things like strong ownership, which are an additional guarantee that you can't get out of hash include, people really just care about the build times a lot of the time. So how do we get better build times out of C++ modules? And what makes the compiler go fast, right? The thing that makes it go fast is the removal of textual inclusion. If you can take parsing out of the equation, the compiler will go very quickly. Reducing disk activity, specifically on Windows, disk activity can be kind of expensive depending on what thing you're trying to hit, what thing you're trying to access. And oftentimes hash include hits this problem where you have to go hit a file, read that file, and then there's another hash include inside that file. But this also applies to modules in that you don't want to read more modules than is strictly necessary. And we'll talk more about that in the demo portion. And finally, you want to reduce template instantiation, because template instantiation is not something that modules can really shield you from. If you have to specialize a template, the compiler still has to go through the process of specializing that template and instantiating whatever members of maybe the class template and perform overload resolution and a lot of semantics elaboration that come along with template instantiations. So without further ado, let's jump into the demo and see what we can do about build times. A few years ago now, I created this blog post where I took a project that I had created and it was using traditional hash includes, and I rewrote it to use name modules instead. And so I went through that process of describing the problems that I ran into and how I fixed them, and finally a couple of build results on how, you know, what the performance was at the time. This, remind you, this was many years ago, and today things are in a lot better shape. And finally, this also used CMake and a very early form of CMake. Now we can use more modern CMake facilities. For example, we can build with Ninja now instead of just Visual Studio 2019. So I'm going to go ahead and clone this project and build it without modules, show you the build times, and then I will build it with modules and show you the build times and see if there's some kind of measurable difference or if they're worth pursuing at all. So I went ahead and grabbed that repo and cloned it locally So let's go ahead and use CMake to configure and build this project so we can sort of get an idea of what it looks like without modules first. So we're going to use Ninja as our generation target, and we're going to add a build folder. Okay, so that's done. Let's build it. So we see here that there's a whole bunch of information that was spit out. So let's kind of clean this up a tiny bit. Let's only modify this file. So I'll add a little bit of white space. And let's go back to here and see what it looks like if we just build that main file. So the thing we want to pay attention to here is the number that was spent in the front end. So that's c1xx.dll, right? We spent 1.3 seconds just building this one file. So that's an example of how long that took. And I'll do a side-by-side of the end-to-end build at the end with the non-modules one and the modularized version, just so you can kind of see what an end-to-end build looks like instead of just the inner loop. So let's switch over to the modules version. So now let's see what CMake looks like here. So let's remove the old configuration directory. And let's reconfigure and rebuild. So let's go ahead and build. So you can see it wasn't that much longer than the like the end-to-end build, including building all the IFCs, wasn't that much longer. But let's take a look at what it takes to rebuild this thing now. So if I make a white space change again, and I come back here, and I say CMake build, right? Now we're seeing some pretty crazy speed up. We see that we went from 1.3 seconds to 0.11 seconds. That is an actual 10x speed up from using name modules over not using name modules and using traditional hash includes. And if you're still wondering if the behavior of the actual application is the same, we can go ahead and go into build here and ballpit.exe, right? It functions exactly the same with modules and without modules, right? So we built the same program just at 10 times faster. And so I realized that was a little bit of a smaller project to kind of sink your teeth into, and it might not be illustrative of larger programs that are not built with CMake and built with other various build systems such as Bazel. But if we kind of look again at the experiment that we did with Office, and we come back to that build throughput graph, we ended up seeing experiences where the module build was actually up to 20% faster than using regular PCH. So we took a technology which was roughly 30 years old at this point, and we improved it to the point where we could make the header units actually faster and more efficient in other ways than header unit or than the PCH ever could be. So if we scroll down to the additional advantages section, we can see that the sizes of the on-disk artifacts is significantly reduced. And this is what I was talking about, where you want to reduce your on-disk I/O, because the compiler does have to read the entire PCH. It has to memory map that in order to make things work. And the same thing is true of the IFC. However, the IFC is roughly 10 times smaller than that of the PCH in almost every case. So the fewer of these things you load in, the fewer memory maps you have to perform, the better your overall throughput will be. Let's come back to our deck one last time. And finally, we have tackled the last myth of C++ modules do not improve your build times to C++ modules do improve your build times. Definitively, we've proven it. And obviously, your mileage may vary there, But in our experience, as long as you're doing things in a way that's very modules friendly, you tend to get this really good throughput benefit. And thank you for joining me today. I hope you were able to learn something that you can take with you and sort of move past some of these common misconceptions that I have gone over with C++ modules. And maybe you can help in the adoption of modules yourself on your own projects and sort of move forward with the benefits of name modules. And thank you all again.
Thanks very much, Cameron. As with the other talks, Cameron is in chat right now, so if you have any questions, please do drop them there. And we're going to swiftly move on to our final talk of today's conference. Hannah is going to be telling us about Constexpr and whether we should or should not Constexpr everything. Take it away, Hannah.
See my screen? Perfect. Okay. Hello, everyone. I'm Hannah. You probably know me from other conferences, but I work for Woven by Toyota in technology and standard team. And I like Constexpr, so that's my personal hobby. And I'm going to talk about it. But first, we start with C++ History 101. Because to appreciate what Constexpr gave us, is important to know what was before. So C++ 19.8/03. Oh, what's happening here? Oh. Something is happening with my slides, sorry. Yeah, okay. So you have vector, 42 elements, not one element of 42. You iterated with iterators. You needed to name it explicitly. There was no auto. So you needed to take two iterators, iterate it, print it. If you want something like compile time expression, you needed to use metaprogramming like macros. So let's have macros square of a, which is a times a, and then you need square of 5, which will calculate 5 times 5. But if you added like some constant like base size, there can be some problems, like 5 plus base size is suddenly evaluated like 5 plus base size times 5 plus base size, which is wrong. It's not obvious for first, like when you look at it. So it's terrible, and I don't like using preprocessor for metaprogramming. But you can use templates, even in C++ 98.03. You can create like a container for type, or you can have like storage of some size, because you can have also template parameters which are not types, but values. But in order to store the size so it will be accessible from outside of the template instance, you need to create a name. And in C++ 98.03, you needed to use enum. It's terrible. And C++ 11, which is 14 years ago, we have auto. So you can initialize variables based on whatever you want. You can iterate range. You have range force. You can create Constexpr functions. So instead of preprocessor macros, you have real functions. And you just calculate it, and it's safe. It will evaluate it only once, and it's doing exactly what you want. But you cannot use any conditional statements, any like control for flow. So no cycles, no ifs. It's just one expression. So you need to be creative. You can use ternary operator. So if it's less than 0, evaluate it to 0. Otherwise, if it's 1, then evaluate it 1. And otherwise, you can do a recursion. And once you have recursion and conditions, you are template complete. So Constexpr in C++ 11 was template complete, but it was terrible to use. So you can also have static Constexpr variables inside of types, it's a little bit complicated. You can static assert on them, like it's just name variable, like constant. You can give like error message, but you need to initialize it, define it outside of class, and that's terrible because it makes impossible to write nice templates or initialize it for any type T. You actually needed to explicitly initialize or define every instantiation on your own outside of the class. This makes it really terrible to write any generic code because you need to do it for int, unsigned. But also you have in C++11, you have lambdas. It's awesome. And they can have control flow, but sadly, they cannot be Constexpr. C++14, to make it a little bit short, you have template Constexpr variables. You still cannot define static Constexpr variables inside of structures, but you can use template Constexpr variables for that. So there is a workaround. And there is a Constexpr function with control flows. You can suddenly have loops, ifs. It's much better word, it's much easier. Yeah, but it's still not enough. C++17 give you if Constexpr, which is not really an evaluation thing. It's more like template metaprogramming thing. It's really useful if you have template parameters for a function, and you can decide what you want based on any template parameter. And you can finally have Constexpr lambdas. C++20, and I'm not describing everything. C++20 give you memory allocations in Constexpr. That was a huge deal. We can finally have stat string, stat vector with caveats that you cannot return them outside of the Constexpr scope. You have also Constexpr virtual functions. And there is a Constexpr relaxation happen. We can finally, Constexpr became more like about its evaluation than its syntax. So if you had a branch inside of your code, and the branch contains something which is not Constexpr compatible, like at the time throwing exception or go to, it's fine. It's fine if it's not evaluated. That makes writing Constexpr code much easier. C++23 give us static Constexpr variables inside functions, which is good because you can reference them in template arguments, and they are not copied on your stack every time you call the function, which is super useful. And Jason Turner had a talk about it recently. I think I saw it in Code Dive, but he did it probably multiple times. There is multiple Constexpr relaxation. Constexpr became more and more about evaluation than about its syntax. And C++26 present, we can cast from and to void star if you have pointer, so we can drag a pointer to type arrays interface, which is useful to implementing function ref and a lot of types of polymorphism. We have Constexpr structure bindings, so you can create Constexpr structure binding on Constexpr variable, so you can access the pieces of it nicely. And there is many more features, but that's just scope of things. And word of the day is caution. Constexpr was designed from the beginning by slowly adding stuff we were comfortable adding. At first, it was just expression because we already had expression in the language, in the enum. But then we added control flows because we became comfortable making control flow. But you can see that it's just once people get used to something, we will bring more. But Constexpr is actually a contract, not like contracts in C++, but contract with library user, if it's in front of function, obviously. It says that your function is able to be constant evaluated, and as an author, you won't break this promise. You won't use anything which will break this function to be Constexpr. At least in before C++ tried to make sure that every possible path is constant evaluatable. Current status in C++ since 23, I think, is that you can write Constexpr function which is not constant evaluatable anymore. So when it's evaluated, when you enter immediate context, there is multiple contexts where constant evaluation needs to happen. In static assert, in non-type template arguments, set array t expression. So if you calculate the expression, it needs to be evaluated as a constant expression. if you initialize or define a Constexpr variable, then it needs to be constant evaluated. If you calling constant eval function and all its arguments are not are constant known, if they are not, the constant eval scope will grow and it will eat your Constexpr functions from it, or otherwise it will give you error. And so look at this example, because if you look at the example, and please tell me in chat how many times function calculate size for is going to be called. Can you guess? Function, or how many times it will calculate some size? How many times function prepare storage will be called? Prepare storage will be called twice, and it will be called in this example in runtime, unless this code is in constant evaluated scope. But the function, it will be called twice in runtime, but function calculate size for will be called only once and during parsing of function prepare storage. Okay. So when you enter immediate context, also for each instantiation, so if you have template Constexpr function in template, every time you instantiate the template function and the argument is depending on template argument, it will be evaluated. So during your compilation of your C++ program, there is multiple evaluation of constant evaluation, and it's running C++ program you wrote, but every time it's called, every time it's evaluated, it's standalone instantiation, which doesn't know anything about other universe. It doesn't know about anything after the part you parsed, and it doesn't know anything about any other evaluation. There is no state. It's always just evaluation which will fold into one value. With reflection, it will change a bit because you can instantiate new types, but that's unfortunate, but also useful. So how is Constexpr code evaluated? In the constant evaluator, which is part of the compiler, and in Clang, because I'm familiar with Clang, and so I'm going to talk about Clang, but are implemented kind of similar way. There is a file expr_constant.cpp, which is C++ interpreter, in basically one file, and it has 17,000 lines of code. You can see it on GitHub. It's fun to read. And it evaluates C++ independent of your C++ CPU architecture. It's just interpreter, and it can change its behavior and give you different behavior based on types of float your architecture supports, but it's not that it's using floats of your architecture or your computer. It's using floats you tell it it's supposed to be used. So it's going to use same float for your target architecture. And also it's implemented for C++ abstract machine. So it doesn't allow to happen anything which is not defined in standard. And if there is any UB or anything which is like invalid expression or something, it's supposed to tell you and give you error. It's very strict, and it's like kind of like really like a really pedantic C++ machine for you. But implemented in all compilers mostly is it just walks over AST. So if you have like operator plus, binary operator, it has two branches, left and right. So it will evaluate a left, then it will evaluate a right, and then it will calculate plus operation. If it's like just literal, it will just do the calculation of plus. Otherwise, it can call a function, which is already resolved, but during parsing, this operator is then changed into call expression. So it's just walking AST. Everything is prepared for it, and it just like giving semantics to all the existing AST, all the cast, all the calls, all the statements, condition, everything is already there. Okay, it does symbolic execution. So if you create integer in Constexpr, it's not integer per se, like 4 bytes or 8 bytes or like bits, but it's something else. If you create a pointer, it's something else. It's not just pointer to memory, it's symbolic pointer. If it's structure, it's not just like a random blob of memory representing your structure. It actually is something which represents the structure much more precisely. This allow the interpreter actually discover all UB like UB you run into or any violation, etc. So symbols representing integer values. You need floating points. You need arrays. You need structures. You need pointers and references. I'm going to tell you how a compiler see them in order to understand how it's evaluated. So what's a value? It can be it's represented with type called AP value, which is arbitrary precision value. I'm not sure exactly. And it can be multiple types. It can be nothing, just initialized. It can be int, which is just store integer of arbitrary precision. You can ask it for integer of 256 bits if you want. You can have float of arbitrary precision. You can have array of other AP values. You can have union of AP value or AP value or AP value indexed by type, which is in union, or indexed by union member. You can have structure, or you can have you can have pointer. Sorry, so and how do you like describing integers and floats? It's kind of obvious, but how do you like describe symbolically array? Inside of the AP value, you have 3 members: data, size, and capacity. And you create capacity 12 in this case. You create array of AP values. You point at the array, which is just C++ program. This is just all implemented in C++. And you can store other AP values in it. And they can be even different types. It doesn't need to be int. It can be float. It can be mixed. It doesn't care. But C++ has only like one type. Union is represented by having AST of the union, and then you have. I'm sorry, something happened again. Okay, union. You have AST of the union, and there is two elements: union of like field and value. And field is pointer to AST. So in this case, I have integer of value 0. And if I set it to something else, it's suddenly another integer from union and different value. These two are different objects, and so the interpreter actually tracks lifetime of your object and lifetime of each member. And if you touch something which is not initialized, if you touch wrong union member, it will give you error because it's not defined. It can be float, it can be structure. And a structure is defined of value kind struct, and you have like multiple structures. And let me do this. Yeah, okay. You have structure, which is data, basis, and number of members. And for this structure, it has only, we have circle, which has parent position, so we have one base. And also we have 3 members: float, color, and color. And data pointer, it points to array of AP values, where first is base of the position, which is just another struct inside. Then there is a float, and there are two another structures as members. That's all. And from the structure itself, there is another structure with 2 floats. With the another structure is another structure, etc., etc. And pointer is the most complicated type to represent, and actually the hardest, because you cannot represent others. Because if you represent others, you can access anything, and then you cannot actually detect if you touch something you are not supposed to. So it's a little bit more complicated. You have object you like point at, and then you cannot use the others, obviously. So you need to use AST location, how the object was created. So you can point at null, obviously. You can point at initialized object. You can point at object, initialized one, or you can point at array on multiple members of each members of the array. Or you can also point past the array. You can point past any object because any object can be represented as a range. And but there are no like numeric addresses. So like symbolic representation of pointers is actually much more closer to standard. They are not ordered. You can compare only pointers representing pointing to same base like object, which is common, and you cannot point to independent objects. So A and B, how do you like sort them? Oh, again, it happened again. Sorry. Yeah, pointer. Okay, ABC, and you cannot sort them. ABC, there's no sorting, and there can be multiple of them and multiple dimensions. It doesn't care. It doesn't matter, and you cannot sort them. So you shouldn't compare pointers which are not pointing at same base objects and array. And for that, it's like really useful to understand pointer provenance. You probably heard this term, and it helps you understand what you can reach from with a pointer. So you have structure of some x, y, z, and you have like some array AP value representing the array. You have another structure of items which contains array and count. But this won't work because you can point past the array and count, and it's not the same object, so you need to represent it a little bit differently. So actually, arrays are sub-objects. You need to think about like original object is having only 2 members, and the array itself is another object inside. And then you have another object on top of that. This is just example. And then you have pointer to the object. That's the object you allocated on stack or heap, whatever, it doesn't matter. But if you take a pointer to a member, you can take pointer to first member of the top object, represented with path.0. And then you can, from there, you can go only down to object inside of the object you are representing. In arrays, you can also go to neighbors, siblings, and obviously you can go down. And from in the arrays, you can go to the left, to the right. You can go past. So it's basically an object you allocated, some name, symbol, A here, and some path. How do you get there? And you can always go only down, and in arrays to siblings. So that's how compiler, at least client, represent a path. I would actually be interested how MSVC does that. But yeah, I will ask probably out someone later. L value and R value. Do we need to represent L value and R value? One is on left, one is on right. It doesn't matter because they are just values, and it's more like property of type, not of the value. R value just means it's marked as a temporary, and you can steal it, but so it's property of C++, not actually values. And R value represent lifetime, so I have like lifetime of global variables, scope-based, lifetime temporaries, and custom heap allocations, which actually can go forever. But if you won't clean after yourself, your program won't be valid constant evaluation because you cannot leak anything. Temporaries can be lifetime extent into scope-based or global-based. So for pointers, identifier of the object is its location in AST. So global variables are identified by its name, AST node, for example. Local variables are identified by AST node and version. So every time you call a function and you get a pointer to local variable, and maybe you return the pointer to local variable, the pointer cannot be used again if you call the function again, like if you leave it. So you need to make sure you can check. So compiler needs to do that. So there is a AST node and version of call. So every time you like go into the function, enter it, version is incremented. And if your version is not matching with function, it cannot work. Allocation values, dynamic allocations, are identified by unique keys, because you allocate them and only like it's just unique key. So it's actually like a key which increments 0, 1, 2, 3, 4, 5, and it goes kind of forever. So pointer is actually a p-value if we have structure of coordinates and some function. So it contains this thing we are going to point at contains two values, and we point at it. So the pointer it's containing the pointer to AST at the actual definition of the variable or declaration, version because it's local variable, and then if you enter again to function, it's other version, etc., etc., etc. And you can also go into submember. So you need path, which is represented as an array of numbers. In this case, it's path to first member and 0. Yeah. So if you have pointer to allocation, dynamic allocation, you have the pointer to expression where it's originated, its key. From the expression, you can deduce type. So a compiler can compare types. So if you have pointer and you try to access it something else, it won't work because it knows the original type. That's how void star cast there and back works. And you have just some key which represent the allocation. You can have obviously pointer to sub-object, and then you need provenance and multiple path, and it's a little bit more like. So if you have like a lot of sub-object in Clang, you will get a long path, and it's and the path actually itself is allocation. So if you want to be, if you want to have a fast Constexpr program, you shouldn't use many sub-objects, but don't do that. Use sub-object; it's nicer. Okay. So what if you have like a global object? So I've pointed to global object into AST, and the value itself is actually inside of it, because AST itself contains the AP value of the object, because global objects, static Constexpr variables or static variables are dragged into runtime and emitted into code. So where are the values stored? Global variables in the AST node, local variables in a stack-like data structure. Allocations are in just.map. And there is a question. If compiler authors designed machine to interpret C++, should all standard library be constant evaluatable? It's like important question. And so let's look at the containers in standard library in C++ 26. Array is Constexpr since 11. BigU is since 26. Flatmap since 26. Flatset since 26. Forward list, same. In place vector, same. Hive. Sorry, when I was writing the paper, Hive wasn't in draft, so we need to fix that. List, Constexpr, map, optional, set, basic string, another map. Everything is val array, not val array. And vector, everything is Constexpr, mostly. So once the interpret is strong enough, and already it's strong enough, we can represent most of the C++ to be evaluated in Constexpr, in constant evaluation. So let's look at the some containers, how they work in detail, but just for fun. So we have stat array, you have object, you have index them, and you need to initialize them. They must be like they can be initialized, and uninitialized value are not allowed. In 23, in 26, they are now allowed with union trick. So we can have iterators back in end. We can have another iterator. We can iterate over the array. With provenance, it's allowed because it's just array. We can modify it because it's just object, and it was work. It's working just easily. So that's the array. We can do that. We can then when it's destroyed, it destroys its members from back. So they behave same as stack variables. So you create like first in, first out, last in. Yeah, it's just like stack. So vector is 3 members, data size, capacity. We can create members. We can move them, but if there is an exception, tables we cannot do that if there is exception during moving. So we actually need to copy it, and then we can copy it safely, then release it. And every time we use like vector and we need more capacity, it's usually like instantiated the allocation with twice more capacity. Some implementation do some different values, but I think like there is like they measure it some number. It's like 1.6 something, but Clang and GCC is doing ×2. So obviously, if you have pointers and you allocate and you create new allocation, iterators will be broken. They cannot reference something which is no longer there, and interpreter can detect that because you iterator internally contain pointer, and the pointer will point at something which is no longer existing, and representation of the pointer in the interpreter allows to detect it without crashing. So you need to move them, and then you have like destroy them from the front. Vector is actually destroying elements from the front, not from the back. That's important. And then you can grow more and continue. And you can have iterators. You can erase element. So you need to move everything, and then shorter size, and you have some capacity still there. You can destroy multiple elements, and it's still all an algorithm based on the number of elements you need to move. There, yeah, and it's destroyed from the beginning again. List is similar. Like you have list, you have like front, back, and every time you create, you need to allocate. So it's not effective data structure, but it's just allocation and it works, and there is no reason why it cannot be Constexpr, and it's not now. It is. So you can have iterator. Iterator is stable when you modify it, or you can pop it. It's O1 operation. You can have iterator in the middle. You can destroy something in the middle, delete it, and then it's deleted. It's safe. Iterator will be moved to the next element. You have in-place vector, which is based on the array. So you have capacity, content, and you have size, and you can put it there. But problem is, at least in C++ 26 until recent meeting, you couldn't let in Constexpr initialize members in array on stack because in-place vector is on stack. So in-place vector for non-default initialized type couldn't be Constexpr. Now we fixed that in the meeting, so it's fine. So you have in-place vector also. Constexpr, you can have deque, which is just like a kind of like vector of leaves, which is like cute data structure, but people don't use it. And it was actually inserted into standard kind of as joke with intention that it will never get into, but it's stuck and it's there. But there is technically no reason why everything shouldn't be Constexpr. Kinda. We have control flow if for a while we have variables. Since C++ working, we can call lambdas in Constexpr. We have trivial default initialization, so you cannot you don't need to initialize every Constexpr like every variable inside of console-related code. You can have try catch since 20, but not like throwing exception. You can change active member of union. It's also C++ 20. Before that, you needed to actually destroy whole union and initialize it from fresh in order to make it work. You can have inline assembly, but you cannot evaluate it. You can have virtual function in Constexpr C++20. You can have Constexpr unique pointer in 23. You can have atomic operations like stat atomic of int or stat atomic of pointers since 26. you can have exception throwing since 26. So you can actually throw exception out of like Constexpr function and catch it, and it's fine. If you throw it and won't catch it, compiler will tell you that it's no longer valid program, because if you need to be in Constexpr constant-related code, all allocation needs to be reallocated and all exception needs to be thrown. If they are not thrown, compiler can use the error message from .wat member of the exception and print nice error message. You can have trivial unions, so you can have an array of initialized members, and it can be contiguous. That was the biggest problem with the in-place vector. 26. We can have virtual bases tentatively in 26. So in future, we can make IO streams, string stream, also Constexpr. We can have Constexpr shared pointer tentatively in 26. Hopefully this Friday it will go to a library wording review. Coroutines tentatively since 29. It passed twice evolution, and it's now in core for 29. It's kind of hard to implement them, but it's useful. Can you use byte arrays as object storage? Not yet, because everything is interpreted as symbols. So you cannot have arrays of bytes and just cast it into something else and hope for the best. Okay, so and then pointer tagging. So yeah, oh, I'm going over time. Sorry, I need to go faster. Pointer tagging, not yet. Reinterpret cast, not yet. So let's look at the wording. Constexpr and constant specifier tackle Constexpr. A function is Constexpr suitable if it's not coroutine, and if the function is constructor or destructor, and its class does not have any virtual base classes. Except for instantiated Constexpr functions, which means templated function, non-templated Constexpr functions shall be Constexpr suitable, which means you cannot write Constexpr function if it's coroutine or if it's a constructor or destructor of type which has virtual bases. Virtual bases are tentatively in 26, so function is Constexpr suitable only if it's not coroutine. So Constexpr is just a limit of execution, not syntax anymore, like with exception of the coroutines. Is still Constexpr in front of functions needed? That's a question for you to think about. Is doesn't mean anything, because look at the constant expression, and expression E is a constant expression unless the evaluation of E following the rules of abstract machine into execution would evaluate on one of the following. There is a list of things which cannot be in order to be constant evaluation. So an invocation of non-Constexpr function. So if you call something which is not Constexpr marked, then it cannot work. If it's undefined Constexpr function, so you have only definition, declaration, but no definition, and instantiation of Constexpr function is not Constexpr suitable. That is not Constexpr suitable. So if every function will be Constexpr suitable once we have coroutines and virtual bases, then this point will be nothing. 10.4, you cannot call undefined function anyway, and non-Constexpr function, it's just one thing which will block us from calling a function which is not Constexpr, just like this one line of standards. So Constexpr in front of function, not important anymore. It was a contract and opt-in into constant evaluation, which was defined by cautious. But now everything kind of be Constexpr, and this opt-in should be maybe just opt-out. In GCC and in Clang, there is a F implicit Constexpr, and I have PR for Clang, and I hope we'll get in, but keep fingers crossed. Then suddenly you are in a world where you don't need to write Constexpr in front of every function. So that's Constexpr everything. Sorry for going over time.
Thanks very much, Anna. So that this is another default that C++ got wrong, then we should just, everything should be Constexpr.
Exactly.
All right, thank you very much. I really enjoyed that talk, and we're now at the end of the conference. So thank you everyone for tuning in, and we will see you next year, hopefully, where we'll have another bunch of talks and pre-conference content. All of these sessions will be going live on the Visual Studio YouTube, so please do go check them out if you want to rewatch some or catch up on any that you missed. And thanks very much for joining. See you next time.